Okay, so this is a quick video about how to use the first law of thermodynamics to find the heat capacity of an ideal gas. So what is heat capacity? Heat capacity basically means that if you add some heat Q to an object, it could be water or some metal or what we're going to look at as gases, you get a change in temperature, delta T. You add energy, the temperature increases. How much does the temperature increase? Well, that depends on what you're adding the energy to, and that's what heat capacity is all about. So C is called the heat capacity, and it's different for every substance. Incidentally, you may have seen this written a little differently. You may have seen this in the past as MC delta T. In that case, they're talking about the specific heat per unit mass. I'm not. We could. It's not a big deal. I'm just saying I want to know the total amount of heat depending on the size of my object, not just per unit mass. But it's the same idea, okay? All right, so what does this mean? You got a box filled with a gas. All the air molecules are plunking around. You add some heat to the box, and what happens? The temperature increases. That's what we discover. And when the temperature increases, the velocities increase. In other words, the gas speeds up. How do I know that? Well, we did all that kinetic theory stuff, and when we did the kinetic theory stuff, we learned that the kinetic energy of a gas is 3/2 kT. In other words, if you increase the temperature, the gas is going to move faster. Okay? But there's not the only thing that can happen when you add heat. There's another possibility. If you add heat, the system can also grow. And what you find is that when it grows, the temperature changes less. So just think about a balloon on a warm day. You blow it up inside, you take it outside, the balloon will expand. Watch it happen. Do the experiment. But what you'll find is that when the balloon does its expanding, the air inside doesn't get as hot as if the balloon didn't expand. And that's actually very curious, particularly for an ideal gas, because we know that the change in energy of an ideal gas depends only on the temperature. But in both cases, we're adding the same amount of energy. We're adding an amount of energy Q, and it seems like the energy of the gas is changing by different amounts. So we must be losing energy somehow. And in a sense, we are. When the gas expands, it has to push whatever is around it out of the way. Whenever you push stuff out of the way, that requires energy. You are doing work on the surroundings. You may say, well, wait a minute, what if I'm expanding into vacuum? Then I don't have to do any work. Okay, yeah, sure, you're right, you don't. But I'm handling the general case where you're surrounded by stuff, and in order to expand into that stuff, you need to push that stuff out of the way, and pushing that stuff out of the way costs you energy. It's work. We are pushing the stuff outside the gas out of the way, so in a sense, we put heat in and work comes out. But if you think about that, that's really just a different way of restating the first law of thermodynamics. However much change in energy the system has, it's how much heat you put in minus the amount of work you get out. Another way to think of that, though, is when you add energy to a system, there's two things that can happen. Its temperature can increase or it can grow. It can grow. And so depending upon whether or not it grows, the specific heat is going to look a little bit different. In general, if we want to write this, we can say this is the change in energy of the system. This is the heat. It is basically defined that way. Talking about specific heat is a way to talk about heat. And here's the work. Okay. Now, depending upon how much work gets done, we're going to have to do different specific heats. And so what I want to look at are two special cases. One is constant volume and the other is constant pressure. You'll see why these are good cases to look at and why these are always the ones that are in the textbook. I mean, they're easy, but they're also very useful. Okay, so let's do constant volume first. For constant volume, I'm going to write the same thing as I wrote above, only now I put a little v there to indicate that I want constant volume. But if you think about it, at constant volume, that means that this guy is 0. You don't change your volume. So the integral over that not changing volume is 0. It's like doing the integral from A to A. It's 0. It's garbage. You can throw it away. That means that we can cross off the delta t's on both sides, and this is super easy. CV is F over 2 times N times R. Notice this doesn't depend on any conditions other than the fact that the volume's constant. I don't need to know what temperature it is. I don't need to know what pressure it is. That's why this is useful constant for talking about a material. Okay, what about if there's constant pressure? Okay, so I'm going to write the same thing, only now I'm going to write CP instead of CV. Now I know I can't chuck the integral in the garbage. The system is going to grow, but it's going to grow at constant pressure. But that's actually good because this is a super easy integral. It means you can take the P outside the integral, P dV, and then that just becomes P delta V. Okay, so I've got this. There's no more integrals or anything to worry about. And if I want to invoke ideal gas law and do a little bit of rearranging, I can. And if I do that, now I have the specific heat at constant pressure. And notice it doesn't depend on anything either. I think the most interesting thing about this is that the specific heat at constant pressure does not depend on the pressure. Does not depend on pressure. That's crazy. It means that somehow the system knows exactly how much to grow so that its temperature will increase at the same rate regardless of what the pressure is. Another way to think of it is, look, when the pressure is higher, it's harder for the system to expand, and so it will plunk more of its energy into increasing the temperature, rather than increasing the volume. Okay, so just as a quick summary, the specific heat at constant volume goes like F over 2 times NR. The specific heat at constant pressure goes like F over 2 NR plus another NR. This is the big equation that everyone likes to put in the textbook. The other thing is, remember, we're talking about the specific heat for the whole system, but often you might be interested in molar specific heat. Molar specific heat, just like you were interested in the specific heat per unit mass or the heat capacity per unit mass. So molar specific heat, then we can just divide everything by N, and then you're looking at Cp equals Cv plus R, which is actually pretty interesting. They're very different situations, and all you have to do is add a gas constant to change the heat capacity. That is definitely worth a thought. Okay, hopefully this was more helpful than confusing.